In June 2025, the first Nvidia GB200 racks began arriving at the Stargate site in Abilene, Texas. Parts of the facility started running while construction continued around them. More buildings were still going up, more electrical capacity was still being prepared, and Nvidia was already shipping the hardware. That scene explains something the headline numbers miss. The AI build-out does not happen in one clean moment. The chips can arrive before the campus around them is finished. Nvidia has since reported more than $81 billion in quarterly revenue. Most of it came from its data center business. So this is not a story about imaginary customers or fabricated demand. Companies are buying the systems. The harder question comes next. At what point does all that genuine buying turn into more computing capacity than the market can actually absorb? To answer that, follow one rack after it leaves Nvidia. A campus like Abilene does not wait until every building is finished and then switch on in one dramatic moment. One hall can begin operating while another is still being fitted out. A group of racks can start working while the next section waits for cooling, networking, or electricity. The final project number describes what the site may eventually become. It says very little about how much capacity is available on one particular day. The buyer also cannot wait until the last cable is connected before placing the chip order. The newest AI systems depend on advanced memory, specialized packaging, and limited manufacturing capacity. If a company waits for the building to be completely ready, it could finish construction and then spend months waiting for processors. So it orders early. That is why racks can begin arriving at Abilene while the wider campus is still taking shape. The customer is trying to prevent one shortage, even if that means accepting another kind of risk. The enormous gigawatt announcements make this harder to track. A gigawatt measures electrical power. It does not measure the number of GPUs. Projects also use the same unit for facilities at very different stages: planned, under construction, partly running, or fully powered. OpenAI's 10 gigawatt target extends to 2029. It is not 1 year of Nvidia production. These figures tell us that companies intend to build an enormous amount of capacity. They do not tell us how much is ready today or how much hardware is already sitting inside it. Early ordering can also spread through the entire supply chain. A cloud company expects AI usage to rise, so it reserves more systems. Nvidia secures more manufacturing capacity. Suppliers prepare more memory, components, and packaging. Every order begins with a real customer request. But the further back you move through the chain, the more the system is preparing for demand that has not arrived yet. Economists call this the bullwhip effect. The danger appears when the forecast changes after everyone has already ordered around it. At this point, the rack has been ordered, the building is caught up, the electricity is connected. It would be easy to treat that as the end of the story. It is not. The servers still need work. They need customers, products, or internal systems using enough computing power to cover electricity, cooling, financing, and the original purchase price. A powered data center is ready to operate. That does not automatically mean it is earning enough to justify what was spent on it. Nvidia may record the product revenue after control of the system passes to the customer. The buyer could still be installing racks, waiting for more power, or trying to fill the new capacity with workloads. Nvidia has completed the part it was paid to complete. The customer's harder test has only started. That is how a genuine chip sale can sit inside an investment whose final return is still unknown. Some systems go straight into operating data centers. Some replace older processors. Some arrive as new halls open in stages. Others move through manufacturers, system builders, and customers that are still completing installation. There is no public map showing when every rack was switched on, or how heavily it is being used. The physical location of the chips is only part of the answer. What matters more is what they are doing once they arrive. And Nvidia's own balance sheet gives us one number worth watching. Nvidia held almost $26 billion of inventory at the end of April 2026. That was roughly $4.4 billion more than it held 3 months earlier. The number deserves attention, but it does not represent one giant warehouse of unwanted GPUs. Nvidia's inventory includes raw materials, partially completed products, and finished systems. The company is also growing quickly, so it needs more equipment moving through production. For now, the number tells us how much of the supply chain is being prepared for future demand. It becomes more worrying when customer behavior changes first. Imagine the large cloud companies begin delaying purchases, reducing capital budgets, or canceling projects. If Nvidia's inventory keeps growing after that, the extra stock is no longer simply preparing for expansion. It is waiting for orders that did not arrive. Inventory by itself does not settle the argument. Inventory rising while orders weaken would be much harder to dismiss. The most immediate constraint is electricity. Data center power demand rose sharply in 2025, while supplies of transformers, turbines, and other grid equipment remained tight. A new chip architecture can reach the market within a year. A large transformer can take several years to procure. Transmission lines, substations, and new generation can take longer again. Abilene can bring its first halls online, but every later stage still depends on physical equipment that cannot be produced through a software update. This expansion can also affect people outside the data center industry. Utilities may need new substations, transmission lines, or generation to serve one large campus. Depending on local agreements and regulation, the operator may pay those costs directly, or part of the burden may become a wider fight over electricity rates. The demand begins inside an AI facility. The infrastructure around it belongs to a much larger system. Now return to one rack assigned to a new hall. It is purchased in 2026. The building takes another 6 months. Full power arrives 6 months after that. By the time the rack begins regular work, Nvidia is already offering a more efficient generation. The original system has not become useless, but 1 year of the period when it was expected to be most valuable has disappeared before it did much work. Companies spread the cost of equipment across the years they expect to use it. That is depreciation. Imagine a company spends $12 billion on servers. If it expects them to remain useful for 6 years, it records about $2 billion of cost each year. If the useful period is closer to 3 years, the annual cost is about $4 billion. The original payment is the same. What changes is how long the company expects the machines to keep earning money. A long delay makes that assumption harder to defend. The release of a faster chip does not automatically turn the previous generation into waste. Older systems can run smaller models, inference tasks, and less demanding workloads. What matters is whether somebody will still pay enough to use them. An older rack that remains busy can be a good asset. A new rack that spends most of its time empty can be a poor one. The important divide is not old versus new. It is busy versus underused. The largest buyers can keep this going for a long time. Their cloud, software, and advertising businesses generate enough cash to fund new facilities while they search for AI products that customers will consistently pay for. A smaller company might be forced to stop after one expensive mistake. These firms can keep building, moving workloads around, and extending the experiment. That makes the boom more durable. It also means weak projects may take years to become obvious. The shift toward excess capacity would probably appear through several signals together. Large customers would reduce future capital spending, chip orders would slow, projects would move from delays to cancellations, providers would cut computing prices to fill unused servers. Nvidia's inventory would keep rising even as sales growth weakened. One signal can have an innocent explanation. The first racks arriving at Abilene tell us the build-out is real. Parts of the site are operating. More capacity is still being added. Nvidia has made real sales into a real construction program. But the first order does not give us the final answer. The answer comes later, when the customer decides how much to buy next. If the existing machines are busy and earning enough, the next order keeps growing. If they are waiting for work, the expansion slows. Projects begin to disappear, prices start falling, inventory begins to accumulate. That is the line between a build-out and an overbuild. The first racks tell us the project started. The next order tells us whether it worked.